today we're working with lesson 8, linear and angular speeds. Remember, this is still target 1B, radian applications. Let's go ahead and first define what we mean by linear and angular speeds. Suppose we have an object that is moving at a constant speed along a circular arc of radius r. So similar to what we had yesterday in our problems, we have a circle, we have this arc length, which is our s, and we're trying to describe how fast it is traveling along this arc. So if s is the length of the arc, and we know it's traveled in time t, then we would describe the speed, or v, of that particle, whatever is traveling along this arc, to be the distance it travels, so arc length over the amount of time it takes. So if you remember from yesterday, arc length we described with s. So we could say it's s over t, but I like to go ahead and write it out, like what s is. So remember, s is radius times our central angle theta over our time. So we have our distance, and then how fast we're traveling that distance will be our speed. So arc length over time, r times theta over time. Now to define angular speed, if we have our theta is our angle corresponding to the arc length s, then the angular speed, which we indicate with a lowercase omega, the angular speed of the particle would be described as our central angle over time. So we still have to, and we don't use that aspect of distance, but we know this central angle creates that arc length s. And how fast that angle changes per time will be our angular speed. So when we're dealing with multiple revolutions, so if we're talking about an object that's spinning round and around and around and around, it can be really helpful to think of theta as the number of revolutions times 2 pi. Because if you remember from our work with radians, we know that 1 full revolution is 2 pi. So if we have 10 revolutions, it will just be 10 times 2 pi. So let's go ahead and look at an example. So we have the second hand on a clock, and we know that second hand is 10.2 centimeters long. We want to find out how far the tip travels in 20 seconds. So first they're just asking us to find the distance. So this would be arc length, right? We're talking about the distance that point travels, that second hand, in 20 seconds. So we're traveling in 20 seconds. How far is that point going? So we'll use our arc length formula from yesterday. S equals r times theta. And we know the radius is going to be 10.2. That's how long our second hand is. So we'll say this is 10.2. And then how far do we go? What is our angle here? So if we look at our second hand, we're starting, it actually doesn't matter where we start. We can just start with wherever we are in the picture. So we know if we're moving 20 seconds, then we would say, what part of the whole circle are we moving? So we know the whole circle, the whole clock would take us 60 seconds to get all the way around, right? It would take 1 minute for the second hand to go all the way around the clock. But we didn't go all the way around. We went part of the way around. So we know it's going to be less than 1. So how far did we go? We went 20 seconds out of 60 seconds, which is another way of saying we went 1/3 of the way around. And we know the whole distance around, or the whole rotation would be in terms of radian would be 2 pi, but we only went 1/3 of the way. So if you think of it, remember our number of revolutions times 2 pi, our theta will be 1/3 times 2 pi. This is how we'll represent theta. Theta is our revolutions times 2 pi. We only went part of a revolution times 2 pi. We'll get 2 pi over 3 radians. Okay, so that's going to be our central angle of theta. So 10.2 times 2/3 pi is going to equal about 21.36. So we'll go ahead and round to the nearest whole number. So 21 centimeters is how far that second hand is going to travel in just 20 seconds. Okay, so that was just arc length and kind of looking at theta in a different way in terms of like rotations or revolutions. So now let's go ahead and find the linear speed of this second hand. Now we're concerned with it as it passes around the clock. So now we're looking at a full rotation. So it passes around the clock one time. This means it's one revolution or one rotation. So one revolution means that we're just taking our theta would be just 1 times 2 pi. So we know our theta is 2 pi in this sense because we just went around one time. That would be one full circle, 2 pi. And to find the linear speed, we can say our linear speed is our velocity, which is arc length over time, which is r times theta over time. Our radius would be 10.2. And we know that we would have our theta is 2 pi. And now let's see, how far are we going? So how much time is this taking? So if we're going around one time, we know that's going to take us 60 seconds. And because we're dealing with the clock, we have to kind of deduce that information. Usually they'll tell us like, hey, it took you 2 hours, or hey, it took 30 minutes or 2 minutes. But since we're dealing with the clock, the problem doesn't have to tell us the time because we can kind of figure that out on our own. So since we went one time around, we know that that means our time is going to be 60 seconds. So again, because we're dealing with the clock. So down here, our time would be 60. That equals 17 pi over 50 in exact form, which is about 1.068. And let's see, our units is going to be our distance. So our distance is in centimeters over time, which is seconds. So again, units are really important. 0.068 centimeters per second is how far or how fast that tip of the second hand is traveling as it goes around the clock. So that was an example of linear speed. Let's go ahead and look at another example. And we have this time a wind turbine. So the blades of a wind turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. So right now we can kind of start looking at, okay, we've got our theta in the making here. We've got our time here. So this will be our time, and we have our revolutions. Okay, so the first thing I'm going to do before I even start looking at what the problem's asking me, I'm going to find theta. So I know theta, remember, is our rotations or our revolutions times 2 pi. So how many times we're moving around times one full circle in radians. So that will be 15 times 2 pi, which is 30 pi radians. So we're talking about multiple rotations here. So that will be our central angle. So I figured that out before even looking at what the problem is. So now what they're looking for is find the angular speed of the propeller in radians per minute. So we want angular speed, so that's how fast our angle is changing. So lowercase omega is theta over time. And we already calculated our theta, so that's 30 pi. And then what was our time? It said 1 minute. So we have 30 pi radians over 1 minute. And in this case, there's really nothing to simplify. And we wanted to find it in radians per minute. So we have radians over minutes. So we could say 30 pi radians per minute will be our angular velocity. For me, I prefer our angular velocity as an exact form. If you also wanted to have it, you could have the approximate also, but I do like to look for that exact. Okay, just it's, to me, it's easier to work with when we're using it in like our linear velocity problems to have that exact number. So now let's go ahead and, so actually let's look at what we found. So we found the tip of, or we found the rate of the angle that it is changing. So as we're rotating around here, how fast is that angle changing? It is changing 30 pi radians per just 1 minute. Okay, so now let's look at finding the linear speed of the tip of the blade. So now we want to take, let's say we have like a caterpillar or something out here. We want to figure out how fast he's traveling as he travels around that wind turbine. So find the linear speed of the tips of the blade as we're spinning around and around and around. So linear speed is our velocity, or our v, equals arc length over time. Arc length is radius times r theta over our time t. So we know from our problem that our propellers are 116 feet long. And we know our theta from before is 30 pi. Now we just have to put in our time. So time was 1 minute. And then we'll kind of see what we have there. So notice how I did keep our units when we're solving. I didn't have our radians in here, but we definitely want to keep our units of our measure for sure. 3,480 pi. And remember, this speed is in feet per minute. So 3,480 pi feet per minute. But what do they want? They want it in terms of miles per hour. So this would be our answer, our exact answer. But now we have to convert from feet to miles and from minutes to hours. Okay, so now I'm going to go ahead and do that down here. So keep it in your exact form. It'll make your conversions a lot more precise and a little bit easier to simplify. So now we're just going to convert. So I'm going to say down here 3,480 pi over 1 minute. And I got to put my feet up there. Just like we did before when we were converting from radians to degrees or degrees to radians, we want to multiply this by a ratio that's going to leave us with the correct units. So I'm going to go ahead and start with time. And I just do it all at once. I write like one big math problem. Some people like to break it down in steps and have some intermediate values along the way. Either way is fine with me. So we have 1 minute. We know that 1 minute and 60, I'm sorry, 1 minute, we're going to hours. So we know that 60 minutes is equal to 1 hour. So those are equivalent units. So we're going to put minutes in the numerator. And we want to do that so our minutes will cancel out. So 60 minutes is equal to 1 hour. So again, we're just multiplying by 1 because 60 minutes is the same thing as 1 hour. So that will leave us with the proper units of time. But now we also have to worry about this feet over here. And we want to go to miles. So feet is in the numerator, so we want to put feet in the denominator, and we're trying to make it equal to 1 mile. So 1 mile is 5,280 feet. We're going to use that one a lot, so I would jot it down somewhere. And now what we can do is start simplifying everything in order to kind of solve our problem. So we can simplify 5,280 and 60. That will give us 1 and 88. We can go ahead and simplify further. We can simplify by 8. So as an exact answer, that would be 435. And let's go ahead and look at our units. We have our feet have canceled out. Our minutes have canceled out. And if you look, we're just left with miles per hour. So this is 435 pi miles over over 11 hours. And let's put that as a decimal. That would be 124.24 miles per hour, or you can write it as miles per hour. Either way is fine with me.